Okay, so I told you that this equation for incompressible liquid, it's called continuity. And right now, you'll always see it referred to as the continuity equation. I think of it as just conservation of mass, because that's what it's doing. But this is a very important one. So, right, this, I should have done it earlier. I hope we all maybe remembered that this vector operator is, right, think of it as a vector of partial derivatives. Right? Right. We'll call it like that. So a dot product creates a summation of terms. So you write it's a dot product with a vector. What do you get? This vector, right? The vector itself is the u velocity, the v velocity, and the w velocity. So if we dot those things together, you can do a component version of continuity, which is this. So these are the components where, right, the vector field had an x component, a y component, and a w component. And that makes it, right, that's making the whole vector. And then we have these x, you dot them together, you get this expression. The first simplification, right, you can do for all fluids is taking dimensions away. So you could have one-dimensional flow, right, and that would take, right, we would take one of these away. It's not really that interesting. 3 is really hard, but a more solvable one is if you take one of the dimensions away, right? So we just say there's no velocity in the w direction just from intuition. You can just reduce this continuity equation to just 2 terms. And it's this 2-term thing that comes up with this idea of a stream function, which I'll get to later. But first, I kind of want to also address with this scaling stuff. How can you say that, right? What's a good estimate of when you can say that this part doesn't matter or this velocity is negligible? So I had a picture in the notes, but I can do it again. If you have some like surface sitting in 3-dimensional space, right? Like this. And this is the width of the plate. And then if I looked, let's say at this little point, maybe right here. Check one up like that. So this will be now my x. This will be my y. And then we'll call this z. So here's just a plane, like versus like a little particle where it's sitting in the air, let's say. Air is flowing over it, right? So I have a bunch of air coming in like this, right? This is all in 3 dimensions right now, but you can see it's all mostly going in the x direction. And you can tell that you could put a little wind, right? The little things on top of houses, right? You could just kind of see how this thing is mostly oriented like this. You could put another one up here, and you have the thing, everything's oriented like that. So most of the velocity is going that way, or it's right. So it's kind of almost behaving one-dimensional. Now, just from this distance right here, if we even zoom in, and this is what we'll do for the external flows, we'll zoom in to like just right around the surface or get really close to that surface area, right? If we're right on that surface area, we'll do this, right? We'll have this situation where we will, once again, we can write out the full dimension. Remember the scaling thing I did where you just turn all of these into algebraic fractions. So you have some u infinity, which is which was right. That's the incoming fluid that we're going to have in some velocity field, and that would be over. Well, how about when we look at a small, right? When we look at some small direction, an L, and then we'll have a Z, which we don't actually know. And then if we're going to zoom in really, really close to this, right? Let's say my field of view is a little bit of an L, and then I'll have this delta bar right here. So if you want some numbers, you could think of this right, say that L, the length of this plate, is like 10 meters long. So maybe you don't really know what this W is, but right, it has the L under it for the scale. And then this velocity for the V, I don't know, but I do know that I zoomed in so close that this delta is, how about it's like 0.5 centimeters. Like that's how close I'm zooming into the panel. So you then kind of say, well, this is a giant number right here, and I haven't observed any like cross flow, right? None of the things measuring fluid velocities are pointed in that direction. So that just can tell you either from the length scale or this being slow, that won't matter. So then you can justifiably say this is now 0. And then if this is right, and then you have this delta right here, this is a really small number. So we then say, well, keep that term around because I divided by a very, very tiny number. So this could be big. That's just an example of how you can use these scales to do these things we always do in fluids class where we cross a term out and say that's not going to be there anymore. But I think it's nice to see it happen here.